And do my best to do this next video. Still getting over this cold, and my voice hasn't quite returned back to its normal. And I'll do my best not to be too sniffly or coughing or anything on it. But anyway, we're going to start by modeling gases, and the first thing we want to talk about is pressure. And pressure doesn't always have to just apply to gases, but it basically is used a lot in it. So we're going to define pressure, and essentially, all that pressure is, we'll use a capital P for it. I'm not sure if your book. Some books use lowercase p's. I'm used to using a capital B, but use lowercase or capital. I'm used to lowercase b and momentum, so I usually use a capital for this, and it's the force per unit area on a surface or a container, and that's pretty much it. The units for it, of course, force is a Newton, area is a meter squared, and this is actually defined then as a Pascal, PA. But basically, for a gas or something like that, if we have a wall here, say we zoom in on some sort of wall, and we have a bunch of gas particles all just moving around randomly here like this, some of them will hit, and as they bounce on the wall, others will go other ways, but they'll be colliding with this wall over here, and those collisions will apply a force to it. And if we average out over the whole surface, so like if we have a whole box or something full of a gas inside, what happens is the box, all the little particles are going to collide with all the walls on the inside, and they're going to just put this outward pressure on it. It's kind of like when you blow up a balloon, the more air you put in there, there's more air in there, there's more collisions with the wall, and it pushes the wall of the balloon outward and makes it get bigger as you put air inside it. That sort of thing. Another way to think about this, just as a quick example, is the old question of would you rather be stepped on by an elephant or by a woman wearing high heels? And so if you go through and do the math out and you look at the area of the pad of the foot of an elephant and a quarter of the elephant's weight, let's say, because if he steps on you, he's putting a quarter of his weight on you, and you compare that pressure, that force per the area of the bottom of the elephant's foot, compare it to someone stepping down you, say a 100-pound person stepping on you with a high heel that's probably like a square centimeter or 2 square centimeters in size stepping down on you. What you'll find is even though this is a much lower force here because it's only 100 pounds compared to the entire weight of an elephant, this is spread out over a much larger area. This is in a much smaller area, and this would actually injure you much more than the elephant would because it would be a much higher pressure from the small area of the heel versus the big spread area. Another example of this is those beds of nails. If you try to lay on one single nail, it's going to stab into you. But if you put a bunch of nails everywhere, make a big giant bed of nails, 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 nails. I don't want to draw them all, but you've seen those things where it's just tons of nails on this bed. Well, then you can lay on that bed, and you're not going to get hurt by it because the while if it's just one nail and it's your force on it, it's spread over just the end of the nail, and it's very high pressure and it stabs into you. Whereas if you have a bed of nails, a whole bunch of nails all over the place, it's your weight spread out over all the nails, and so they each have a very low pressure because you have a much bigger area because you have a bunch of nails rather than just one. So just some ideas to think about pressure. We're more interested in the version with the gas rather than these other two, but they're still essentially the same. So some experiments were done with pressure and volume and temperature, and the first one held temperature constant and varied pressure and then measured what volume occurred, and it was found that they were inversely proportional to each other. So this was a constant temperature, so the pressure varied the pressure, and they was inversely proportional. So pressure was inversely proportional to volume. And then another one was done where they showed they varied temperature and measured volume with a constant pressure. So just the only other version, they found that they were linear, and in fact, this went back to the origin. This was one of the ways I believe in the last video I talked about how they found absolute zero, or how Kelvin used to find absolute zero. But anyway, this tells us that volume is directly proportional to temperature, And then the last third experiment we can do is, well, we held temperature constant and pressure constant. The last experiment that was done is to hold volume constant. So constant volume, and then as you vary temperature, what happens to the pressure? And again, that's another linear relationship that could be extrapolated back like that again, and this would also tell you the absolute 0 point as well. So here, pressure is proportional to temperature, directly proportional to it. And so looking at these three things, we can put them together and say that pressure is proportional to temperature and volume is proportional to temperature. So we can actually multiply them together, and if we took and divided this over, you could have P is proportional to T over V. That gives us that pressure and volume are inversely proportional, and so this one little idea right here tells us, in this little order, is basically putting all three of these together. Pressure times volume is proportional to temperature. Okay, and it turns out all we really need to do is just add some constant here, and then this works really well. So then what is this constant? It turns out that constant is something, when we put that constant here, something we call the ideal gas law. And we'll talk about what an ideal gas is in just a little bit. But basically this law, even for no gas is actually going to fit the ideal gas law. It's a perfect kind of situation. But most gases are very close to it. So this is a very good approximation for most gases. Better for some than others, but it's pretty good. It's the ideal gas law, sometimes called the equation of state. It's I don't really like to call it that because there are multiple equations of state. So this is one equation of state. It's not the only one, but it is the equation of state for ideal gases. And so basically we get this: PV, pressure times volume, equals little n, big R, and T. And then there's another version you can do: PV equals big N, KB, and then T. So our constant is either going to be this little n times r or capital N times kb. And if we think about this, what are these n's? Well, both these n's refer to the amount of substance that you have. Of course, the more substance you have, the higher pressure is going to be. So that's going to be proportional to it, so it's good to put that there. And then this r and this kb, they're actually just constants of proportionality. And we'll talk about those in a minute. So, but let's look at first this n versus this n. I said they were both telling you how much of something you have. You imagine that as you pump more and more gas into a box, that pressure is going to go up. So if I have a box here and I put two atoms in it, they're going to occasionally bump into the walls, and that's not going to be a lot of pressure. But if I start putting tons of particles all in here, the more I put in here, the more particles there are to collide with the walls and add to that pressure, so the pressure goes up. So that's why we have these amount of somethings here. But so what are these? Well, this here is called this n is the number of moles of a substance. Okay, a mole, which I'm sure you've probably learned in another class, is every time you have what's called Avogadro's number. We'll do n sub a. It's 6.022 times 10 to the 23rd particles. Okay, give or take a few million billion. It's just an approximation, but basically the idea is if you have this many particles of something, it could be this many atoms of hydrogen or this many molecules of water. It's a particle, so it's either an atom or a molecule, but it tells you that every time you have one of this many of those, you have 1 mole. Okay, so how would you figure out how many moles you had? You would say, all right, here my number of moles is going to be my total number of particles that I have, number of total particles, divided by Avogadro's number. This is kind of like if I tell you that there are 12 eggs in 1 dozen eggs, and then I tell you have 36 eggs. How many dozen eggs did you have? You would do your total number of eggs, 36, divided by the number of eggs in 1 dozen, 12, and you'd have 3 dozen eggs. Well, it's the same thing here. You have 6.022 times 10 to the 23rd particles in a mole, and you have this many particles. Divide them, and you've got what it is. Well, we don't have to write total number of particles like that. What we can really do just write is this capital N. So we can say N is equal to capital N over NA, and that tells you that this capital N is equal to your total particles, total number particles, okay? And that's what that is. So here, total number of particles, here, number of moles that you have. And then how about these two constants? They're just constant proportionality. This R is called the gas constant, or sometimes the ideal gas constant. So R is the gas constant. And KB is called the Boltzmann. I believe I'll spell this right. Boltzmann with 2 N's is the Boltzmann constant. And they're both very much related and very interchangeable. And we can figure out how they're related just by doing this. Well, if PB and T have to be the same, that means this little constant here has to equal this little constant here. And we've got that NR equals NKB. So number of moles times R has to equal number of particles times KB. And then we can replace this N with N over NA. R equals NKB, because remember that's how the number of moles relates to the number of particles. And we've got then the N's cancel, and we've got that R is equal to, oops, sorry, I forgot to write KB. I wrote that B there, sorry. NKB, we've got R is equal to Avogadro's number times the Boltzmann constant. Okay, and I'm sorry I didn't write down what the values of those two were, but you can look it up probably in the front or back cover of any book, or a quick Google search, and you'll get the value for both of those. I apologize I didn't write it down, but it's really easy to find. They're just constant numbers that'll fix these up and fix our units, just like normal constants of proportionality do that we've seen previously. And so that's the relationship between these two, and you can go back and forth between the two versions of this equation just by doing that. I can't get that to erase very well. So I'm just going to put a box around it. This PV equals nRT. This is the guy you really need to know, but you can also use this form of it as well. I believe this is the one you would be given in your data booklet. So there, PV equals nRT. Good thing to use. So what gases does this actually apply to? What is it that makes a gas an ideal gas? So let's try this. So first off, an ideal gas, for the particle size, it has basically zero for the size of the particles. They have no volume, basically. So the particles all have a size of 0. This is just to make it what's called a non-interacting gas, or a low, very low interacting gas. That combined with this, 0 forces, I should say 0 ranged forces between particles. They're only allowed to collide and bounce off each other. So there's no ranged forces between them. So we're not worrying about electromagnetic or any of that kind of interaction between them. In reality, there is always some sort of interaction, but it's so small it's very negligible. They follow Newton's laws. They are Newtonian, follow Newton's laws, which is, they're inertial. They keep going in straight lines. They they apply forces to each other to give us pressures, and for every time they apply a force is applied back to them. So they follow Newton's laws. They have a random motion to them. It's not some predictable kind of motion when we first walk up to a system. They're bouncing all over the place, so it's very random in nature. All the collisions between particles, and so particle-particle collisions and particle and wall collisions are elastic, perfectly elastic. We're not losing any energy. If you think about it, where's the energy going to go? They collide. What's going to produce heat? Well, they are already the thing that would hold the heat down on that side. The internal energy would be that heat, and so they're not going to lose anything in these collisions. No energy loss due to that because there's just nowhere for it to go. It's going to turn into heat, which is just vibrant particles, which is just they're the particles. So, and then the collisions occur. The collisions are instantaneous. So instantaneous collisions, they occur immediately. There's not long drawn out collisions. Now, again, all of these aren't necessarily true, but they're all close enough to being true that this works very well. So this idealized situation we're talking about here, PV equals nRT will work. When do we get this situation occur? When we have small particles. All right, small particles under low pressure, so that reduces the number of collisions. We don't have really high pressure with particles all bunched really close together. They're very spread out, they're very small, so they don't interact much, and a relatively high temperature. They're not extremely cold, they're not extremely hot, but they're at a decent temperature. Okay, and most gases fit this very well. There's just the more you get away from these approximation criteria, the less it will fit that pretty well. So let's give an example here. Let's say you were, I don't know, playing in the AFC Championship game, and you decided that you were going to go with the league minimum from the NFL of a 12.5 psi for your footballs, and you filled these footballs up inside at 300 Kelvin, which is about room temperature, so right around 300 Kelvin. And then you took these footballs outside, played with them in cold, wet rain, near kind of freezing type temperatures where you went outside. All right, so this is T inside, and you went outside where the temperature was about 282 Kelvin. It was much colder. And then at halftime, someone decided to check all the pressures in your football. What would they find when they did this? So this is a little quick example we'll do of ideal gas law. So we're going to start with PV equals nRT. In this case, the volume is going to stay constant because the size of the football isn't really going to change. So what we're going to do is we're going to try and put everything that changes. The temperature changes, the pressure is going to change, and the volume in N and R are not going to change. There's not going to be any leaking air, so that'll stay the same. So what we can write is that P over T is equal to NR over V. N is a constant, R is a constant, V is a constant, so this is just a constant. That means that P, the pressure inside over the temperature when you are inside, is equal to the pressure outside over the temperature outside. And if we go ahead and calculate what the pressure would be outside in the cold, once the balls got cold, it would be pressure in over temperature in times the temperature outside. And so the pressure inside, 12.5 psi, pressure pounds per square inch, what that stands for, that kind of psi, different than the Pascal we have up again. This isn't an SI unit, I should probably point that out. The temperature inside was 300 Kelvin, and the temperature outside was 282 Kelvin. And so what pressure would we expect them to get when they checked it at halftime? And this turns out to be 11.75 psi. Now, I'm not saying too much about any particular reason why I'm bringing this up, but if you were to look into it, you would find that the average pressure at halftime for the Deflategate footballs was right around this. All right, it was right here in this range. And so, given uncertainties of different pressure instruments that they used, you could see how, as far as I can tell, basically, even if they had tried to deflate the footballs, then they did a bad job because the footballs at halftime were exactly where you would expect them to be, with a drop in pressure of about probably somewhere in between a half a pound to a whole pound of pressure dropped. Of course, the balls were wet and stuff like that can contribute to a further dropping than this, but that really is pretty much right around what the average temperature or the average pressure was found at halftime. So, not claiming I'm a big Patriots fan, but there you go. It's interesting. Um, I won't say any more about it, but feel free to look into it, think it through. I really don't think something was done here, because if they had done something, then the pressures they would have measured halftime would have been much lower than that one. Okay? And so the last thing I want to talk about is the average kinetic energy inside a gas. And so what we want to do is look at a container. I'm going to do a quick little hand wavy kind of derivation of this. If you want a better, a little more thorough derivation, you can look in your book, but I don't need to go through all that because you're never going to be asked to derive this again. But the average kinetic energy in a gas is 3/2 kBT. Okay, and there's that Boltzmann constant again. So I just want to kind of tell you where this 3/2 comes from. kBT, if you multiply these together, it basically gives temperature or the units of energy because it's not quite energy. But for a kinetic gas, is a very close approximation to the amount of average energy in the gas. And so what we can do here is if you look at just a particle, one particle bouncing back and forth, it's going to bounce off two walls, let's say. Let's just say it's just bouncing back and forth. It's going to bounce off this wall over here and this back wall over here. And so that's where this 2 comes from. It's this one particle split between these two walls. But then as we add more particles in, you have to remember there's those two walls, they're a pair of walls. There's the top and the bottom. And then there is the front wall, and it's getting kind of messy, and that back wall back there. Okay? So there's 3 pairs of walls. The sides, the front and back, and the top and bottom, and that gives us the 3 there. So that's basically, that actually is where these come from. You can go through the whole derivation, but it's just, there you go. You pretty much just have to know how to be able to use that for the average kinetic energy, in a gas right there. Okay? I think that's pretty much all I wanted to go through for this section, and you should just kind of go and work on some problems and see how you do. All right, that's everything. Actually, remembered one thing I wanted to say more to this equation. So this is your average kinetic energy. It's basically your average kinetic energy per particle. So if you want the total kinetic energy of all the particles in your system, it's just one little extra thing you can do, and that's just multiply this. So like the total kinetic energy, like the net in a gas is 3/2 in kBT. Okay, I forgot to tell you that on that last one, but that should make sense. If this is the amount of energy per particle, so Ke per particle, then this would be the total kinetic energy, total Ke. Okay, just keep that. So that should make sense. You're just multiply it by the total number of particles you have. This is per particle, multiply by particles, you've got it. Okay, I'll add this onto the other video so it doesn't have to be a separate video. Okay, that's it.